On December 19th, 2025, at exactly 2:40 a.m., every Schumann resonance station on Earth recorded the same thing: a 25 hertz pulse, clean, precise, impossible to dismiss. 3 hours later, 3i Atlas, an interstellar visitor, made its closest approach to our planet. Coincidence? Maybe. But here's what they're not telling you. 2025 released more seismic energy than any year since 1960. Hundreds of earthquakes, multiple magnitude 8s, and yet, no big one. The energy is still there, waiting, accumulating in fault zones we can't see. That signal wasn't random. It was specific. And if you stay until the end, you'll discover why what happened on December 19th might be the prologue, not the conclusion. This story isn't over. Hit subscribe so you're here as the data continues streaming in, and as we track whether that 25 hertz pulse was a warning or a countdown. The planet is telling a story, and this channel is decoding every chapter. You probably didn't notice it. Why would you? You were asleep, most likely, or scrolling through your phone, unaware that at exactly 2:40 a.m. coordinated universal time on December 19th, 2025, something happened. Something that shouldn't have happened. Something that makes a lot of scientists extremely uncomfortable when you ask them about it directly. 3 hours and 20 minutes before the interstellar visitor 3i Atlas made its closest approach to Earth, monitoring stations around the planet recorded an electromagnetic anomaly. Not a glitch, not interference, a signal. A clean, precise 25 hertz spike that appeared on instruments designed to measure what we call Schumann resonances. If you've never heard of those, don't worry. Most people haven't, but you're about to understand why this matters more than almost anything else that happened in 2025. Imagine the space between Earth's surface and the ionosphere, that electrically charged layer of atmosphere about 60 miles up as a cavity, a spherical shell of air and electromagnetic potential wrapping around the entire planet. When lightning strikes anywhere on Earth, it sends electromagnetic waves rippling through this cavity. These waves bounce around, circling the globe, interfering with each other, creating standing wave patterns at specific frequencies. The fundamental frequency is about 7.8 hertz. Higher harmonics appear at roughly 14 hertz, 20 hertz, and so on. We call these Schumann resonances, named after the physicist who predicted them in 1952. These signals are always there, like a planetary heartbeat. They're broad, fuzzy, spread across neighboring frequencies, because thunderstorms and lightning don't produce pure tones. They produce noise. Beautiful, chaotic, natural noise. Except on December 19th, 2025, at 2:40 UTC, the signal wasn't broad. It wasn't fuzzy. It was a spike. A narrow, clean, 25 hertz tone that stood out from the background like a laser beam cutting through fog. You might be thinking, so what? Anomalies happen. Equipment malfunctions. Solar flares cause weird effects. Sure. Except this wasn't picked up by one station. Multiple monitoring sites detected it, and the characteristics don't match any known natural source. Thunderstorms create what we call broadband emissions, spreading energy across many frequencies at once. Solar disturbances affect the entire electromagnetic spectrum, not just one specific frequency. This was different. This was precise. 25 hertz sits in a frequency band that some researchers, the ones working in the margins of mainstream geophysics, associate with earthquake precursors. Not universally accepted science, mind you. Not textbook material. But there's a body of experimental work suggesting that ultra-low frequency electromagnetic emissions can occur before large seismic events. The theory involves piezoelectric effects in quartz-rich rocks under extreme stress, generating electrical charges as the crystal structures deform. It's speculative, it's controversial, but it exists. What makes the 25 Hz signal even stranger is that it appeared primarily on vertical polarization. Think of electromagnetic waves like ropes being shaken. They can oscillate side to side, horizontally, or up and down vertically. Most atmospheric disturbances, the kind caused by weather, produce horizontally polarized signals. Vertical polarization suggests the source was beneath the ionosphere, possibly originating from the ground itself. Now let me take you back 11 days earlier. December 8th, 2025. The Sanriku region off the coast of Japan experienced a magnitude 7.6 earthquake. Significant, destructive, tragic. In the days before that quake, some fringe researchers claimed they detected subtle disturbances in electromagnetic monitoring channels. Nothing definitive, nothing that would hold up in peer review. But afterwards, looking at the data, some patterns seemed to emerge. Patterns in the ultra-low frequency range. Patterns around 25 Hz. Most of the world's attention during that week was focused on the sky. 3I Atlas, an interstellar visitor, a cosmic wanderer from beyond our solar system, was approaching its closest point to Earth. News outlets covered it. Amateur astronomers pointed their telescopes upward. Scientists calculated trajectories and analyzed spectroscopic data. It was exciting. A visitor from the stars. Meanwhile, down here, beneath our feet, something was building. And at precisely 3 hours and 20 minutes before 3I Atlas reached perihelion, the planet responded. Some theorists, and I want to be clear that we're entering speculative territory here, suggest that what we detected wasn't random noise at all. They propose that Earth itself generated an electromagnetic pulse, a TAI, planet-scale electrical discharge, a signal that propagated through the magnetosphere and ionosphere, a planetary ping, not passive reception of solar radiation or cosmic rays, but active emission, Earth calling out, or Earth being called to. The uncomfortable question nobody wants to ask publicly is this: why would the planet produce a specific, narrow frequency emission at exactly that moment? Why 25 Hz? Why precisely timed with the approach of an object from interstellar space? Coincidence is always the safest answer. Coincidence doesn't require new physics. It doesn't challenge our understanding of how the universe works. But coincidence also doesn't satisfy curiosity. It doesn't explain the pattern. Because here's what they're not telling you on the evening news. Earth's electromagnetic system wasn't passive that night. Something excited it. Something specific. Something localized in frequency space. Something that conventional atmospheric science doesn't fully account for. You can call it an anomaly. You can call it a glitch. You can call it noise. But when you look at the characteristics, when you examine the timing, when you consider what happened in the weeks before and the months ahead, you start to realize that calling it noise is just another way of saying we don't understand it yet. The signal was real. The instruments don't lie. The question is what it means, and whether it was the first word in a conversation we're not ready to have. Let me tell you about a number that should terrify you. Not because it's huge, not because it's unprecedented, but because of what it represents and what it hasn't yet become. 2025 released more seismic energy than almost any year in recorded history. We're talking about energy equivalent to hundreds of nuclear weapons detonating simultaneously across multiple fault zones. Hundreds of earthquakes above magnitude 5. Multiple events exceeding magnitude 7. And one absolutely monstrous rupture that barely made international headlines because it happened in a remote location where cameras couldn't capture the devastation. August 3rd, 2025. The Kamchatka Peninsula in far eastern Russia. Magnitude 8.8. One of the strongest earthquakes ever recorded. The 9th most powerful quake in human history. The ground shifted so violently that seismometers on the opposite side of the planet detected the shockwaves. Buildings that had survived decades of lesser tremors collapsed. Tsunamis radiated across the Pacific. And yet, if you weren't actively following seismic news, you probably missed it. Because Kamchatka is remote. Because the population density is low. Because our attention spans are short and our news feeds move fast. But that wasn't even the only monster. Myanmar, January 9th, 2025. Magnitude 7.7 to 7.9, depending on which agency you trust. A massive strike slip event. The kind where two tectonic plates grind horizontally past each other, releasing decades or centuries of accumulated stress in seconds. The devastation was regional. The death toll was significant. The implications were global. Then, there's Drake Passage, the stretch of ocean between South America and Antarctica. Multiple significant events throughout the year. Magnitude 7.5. Magnitude 7.8. Earthquakes in places where most people don't live, but where the Earth's crust is actively rearranging itself. Japan experienced several magnitude 7 events. The Ring of Fire, that horseshoe of tectonic boundaries encircling the Pacific Ocean, was unusually active. Not catastrophically so. Not apocalyptically. Just consistently, relentlessly, energetically active. Now let me put this in perspective. The strongest earthquake ever recorded was the Valdivia quake in Chile on May 22, 1960. Magnitude 9.5. It released so much energy that it literally changed the planet's rotation slightly, shortening the day by microseconds. It triggered tsunamis that killed people in Japan and Hawaii. It reshaped coastlines. It remains the benchmark against which we measure seismic catastrophe. 2025 didn't produce a 9.5. It didn't produce a single earthquake that rivals Valdivia in magnitude. But here's the thing about earthquakes. Magnitude is logarithmic. A magnitude 8 earthquake releases about 32 times more energy than a magnitude 7. A magnitude 9 releases 32 times more than a magnitude 8. So when you add up all the seismic energy released across multiple magnitude 7 and magnitude 8 events throughout 2025, the cumulative total approaches the energy output of the most intense seismic years on record. Except it's distributed. Spread out. Released in chunks across different fault systems instead of one catastrophic rupture. Think of it like a debt ledger. Tectonic plates accumulate stress over years, decades, centuries. They're constantly pushing against each other, grinding, deforming, storing elastic energy in the rocks. Eventually, something has to give. The stress gets released. The ledger balances. Usually, this happens through isolated large earthquakes. One big event pays down a huge portion of the accumulated debt for a given fault zone. But in 2025, something different happened. The planet seemed to be making lots of small payments instead of one large one. The energy was being released, yes, but incrementally, which raises an extremely uncomfortable question. If the total energy output is historically high, but no single event has yet matched what the cumulative stress might predict, what happens to the remainder? Where's the rest of the payment? Geophysicists will tell you, correctly, that tectonic processes are variable. Stress doesn't accumulate uniformly. Fault mechanics are complex. Some zones release energy through slow slip events, barely, perceptible shifts that happen over days or weeks instead of seconds. Some release it through swarms of smaller quakes. Some build and build and build until the rupture is catastrophic. There's no universal pattern. Nature doesn't follow a schedule. But there's a psychological weight to knowing that the Earth has been extraordinarily active, that the energy release has been immense, and that the biggest single event we might expect from such a pattern hasn't arrived yet. It's like watching a pot of water that's been boiling furiously without yet boiling over. You know the energy is there. You know something is happening. But the climax hasn't occurred. Scientists emphasize variability. They emphasize that just because 2025 was active doesn't mean a magnitude 9 is imminent. Probability doesn't work that way. Earthquake forecasting is notoriously difficult. We can identify which faults are capable of large events. We can estimate recurrence intervals, but we cannot predict the exact time and place. Anyone who claims otherwise is selling something. And yet, the communities who track these things, the amateur seismologists and the conspiracy theorists, and the genuinely concerned citizens monitoring USGS websites, they all feel it. The unease. The sense that the energy ledger for 2025 is full but unresolved. The Earth has been screaming all year, but the loudest scream hasn't happened yet. Which brings us back to December 19th. 3 hours and 20 minutes before 3i Atlas reached its closest approach, that 25 hertz signal appeared. Not random, not noise. A specific frequency associated, however speculatively, with seismic precursors. Detected globally. Timed with an interstellar event, arriving in a year of unprecedented cumulative seismic energy release. You can dismiss it as coincidence. You can argue that correlation isn't causation, that the human brain is wired to see patterns even in randomness. You'd be right to be skeptical. But you'd also be ignoring the fact that the energy hasn't been paid off. The bill is still open, and the signal came at exactly the wrong time to be ignored. Electromagnetic signals have fingerprints. If you know what to look for, you can identify the source just from the characteristics. Lightning produces a specific signature. Solar flares produce another. Power line interference looks different from auroral activity. Equipment malfunctions have telltale signs. Experienced researchers can glance at a spectrogram and tell you what they're looking at. So when multiple monitoring stations detected that 25 hertz spike on December 19th, 2025, the first assumption was equipment malfunction. Someone plugged in a vacuum cleaner. A transformer nearby was failing. Local radio interference. Except the signal appeared at geographically distributed sites. Different continents, different equipment manufacturers, different local power grids. A coordinated equipment failure across multiple independent systems seems unlikely. The second assumption was atmospheric. Maybe an unusual thunderstorm pattern. Maybe ionospheric currents interacting in a strange way. But atmospheric disturbances produce broadband emissions. When lightning strikes, it doesn't generate a pure tone. It generates a chaotic burst of electromagnetic energy spread across a wide frequency range. You see it on instruments as a fuzzy blob, not a sharp line. The 25 hertz signal was sharp, narrow, precise. Imagine the difference between white noise, the static hiss from an untuned radio, and a single musical note played on a tuning fork. Both are sounds. Both are vibrations. But one is chaos, and the other is order. The 25 hertz signal was ordered. Some researchers have previously noted narrow, low-frequency electromagnetic anomalies appearing before certain large earthquakes. Not consistently, not reliably enough to use for prediction, but occasionally, in the noise of electromagnetic monitoring data, clean spikes appear days or hours before major seismic events. The mechanisms are debated. Piezoelectric effects in stressed rocks, changes in groundwater conductivity, radon gas emissions affecting atmospheric ionization. None of these explanations are universally accepted. All of them remain controversial. But they exist. The data exists. The observations exist. What doesn't exist is a comprehensive theory that ties it all together. We have glimpses. We have correlations. We have case studies. We don't have laws. We don't have equations that predict when and where these signals will appear. We're still in the descriptive phase of science, cataloging observations without fully understanding the underlying physics. Instrumentation artifacts, the false signals generated by equipment problems, usually look different. They tend to reflect the 50 or 60 hertz frequency of local power supplies. They appear as harmonics, multiples of the fundamental frequency. They're often intermittent or correlated with specific user actions. The 25 Hz signal didn't fit any of those patterns. It appeared. It persisted for a measurable duration. It vanished. Clean. Precise. Unexplained. This is where some speculative thinkers enter what I'll call the uncomfortable territory. They propose that Earth itself, when subjected to extreme tectonic stress, can generate electromagnetic emissions. Not as a side effect, not as incidental radiation from physical processes, but as something closer to a diagnostic signal, a planetary self-diagnostic. The idea is that when large fault systems approach critical stress thresholds, the deformation of rock, the movement of fluids, the changes in electrical conductivity all combine to create coherent electromagnetic emissions at specific frequencies. It sounds absurd until you remember that we already know rocks can generate electrical charges when stressed. The piezoelectric effect is well documented. Quartz crystals, when compressed or deformed, produce voltage differences across their surfaces. Quartz is abundant in Earth's crust. Fault zones are often rich in quartz-bearing rocks. Apply enough stress, deform the crystal lattices enough, and you generate electrical potential. Scale that up to a fault zone, hundreds of kilometers long, and suddenly you're talking about significant charge separation, significant electric fields, significant electromagnetic emissions. But why 25 Hz specifically? Why not 10 Hz, or 40 Hz, or some random value? This is where the data gets thin and the speculation gets thick. Some propose that the frequency is determined by the geometry of the fault zone, the way the physical dimensions create resonances in the electromagnetic field. Others suggest it's related to the timescales of the physical processes involved, the rates at which stress accumulates and releases. Nobody knows for sure. What makes the December 19th signal particularly unsettling is the timing. Exactly 3 hours and 20 minutes before 3I Atlas' closest approach. You can argue that this is coincidence, that the two events are unrelated, that one is terrestrial and one is extraterrestrial, and there's no physical mechanism linking them. You'd be arguing from a position of established science, but you'd also be ignoring the fact that science doesn't yet understand all the variables. The uncomfortable question, the one that makes scientists shift in their seats and choose their words carefully, is this. Why does Earth seem to emit a specific frequency associated with seismic stress at precisely the moment an interstellar object reaches its closest approach? If it's coincidence, it's a remarkable one. If it's not coincidence, then we're missing something fundamental about how cosmic events and terrestrial geophysics interact. Some researchers won't even entertain the question. They'll tell you flatly that there's no mechanism, that gravitational effects from 3I Atlas were negligible, that electromagnetic coupling across interplanetary distances is too weak, that you're seeing patterns in noise because the human brain evolved to see patterns. They're not wrong. The burden of proof is on anyone claiming a connection. Extraordinary claims require extraordinary evidence. But the signal existed, the timing was precise, and the year 2025 had already demonstrated that something unusual was happening with Earth's tectonic energy budget. When you combine those facts, when you hold them together and examine them honestly, you're left with a question that doesn't have a comfortable answer yet. What if we're observing coupling mechanisms we don't understand? What if the variables we've been ignoring are the ones that matter? There's a concept in geophysics called lithosphere-atmosphere-ionosphere coupling, LAC for short. It's exactly what it sounds like. The idea that Earth's solid crust, the atmosphere above it, and the ionosphere at the edge of space aren't isolated systems. They talk to each other. They influence each other. They form a coupled system where disturbances in one layer can propagate to the others. The mechanism works something like this. Deformation in the lithosphere, the rocky outer shell of Earth, changes stress patterns in rocks. Stressed rocks can emit gases, particularly radon, which is naturally present in many geological formations. Radon is radioactive. It ionizes air molecules as it decays. Changes in atmospheric ionization affect electrical conductivity. Changes in electrical conductivity alter how the atmosphere couples to the ionosphere electromagnetically. Disturbances in the ionosphere show up as changes in radio wave propagation, in GPS signals, in electromagnetic field measurements. It's a chain of causation. Rock stress leads to gas emission, leads to atmospheric changes, leads to ionospheric disturbances. Each step is physically plausible. Each step has been observed in laboratory conditions or localized field studies. What's controversial is whether this chain operates on large enough scales and with enough reliability to be useful for earthquake monitoring or prediction. The data is mixed. Some studies show correlations, some don't. The scientific community remains unconvinced, but 2025 wasn't a normal year for solar activity either. Solar cycle. 25, the current phase of the sun's 11-year activity cycle, has been unusually energetic. Large sunspots, frequent solar flares, multiple coronal mass ejections hurling billions of tons of charged particles toward Earth. The magnetosphere, our planet's magnetic shield, has been repeatedly compressed and disturbed. Auroras have been visible at lower latitudes than usual. Radio communications have been disrupted. Satellites have experienced problems. Solar activity affects Earth's electromagnetic environment directly. Charged particles from the sun interact with the magnetosphere, inducing currents in the ionosphere, creating fluctuations in ground-level magnetic fields. These fluctuations drive what we call telluric currents, electrical currents flowing through the conductive layers of Earth's crust. Telluric currents are always present to some degree, driven by natural variations in Earth's magnetic field. But during periods of intense solar activity, they can intensify significantly. Now here's where it gets interesting. Telluric currents flow through the same rocks that are under tectonic stress. They interact with the same fault zones that might be accumulating energy. Some researchers have proposed that changes in telluric current patterns could either trigger or inhibit seismic activity by altering the electrical charge distribution in fault zones, potentially affecting friction or pore fluid pressure. It's speculative. It's not textbook geophysics, but it's based on real physical principles. So you have LAIC coupling operating from the ground up, potentially creating ionospheric disturbances before earthquakes. You have solar forcing operating from the top down, driving telluric currents through seismically stressed rocks. And you have 2025, a year of both unusually high seismic energy release and unusually active solar conditions. The two systems are being driven simultaneously. And then 3I Atlas enters the picture. Not just a passive chunk of ice and rock drifting through space. Observations showed that it was actively outgassing, releasing material as it approached the sun. Comets do this. It's normal, but outgassing creates a coma, a cloud of gas and dust around the nucleus. That coma interacts with the solar wind, the stream of charged particles flowing from the sun. It creates a magnetic field environment. It generates electromagnetic disturbances on a small scale. 3I Atlas wasn't close enough to Earth for direct gravitational effects. Even large asteroids passing nearby don't exert measurable tidal forces on our planet. But electromagnetic interactions operate over different length scales. Solar wind disturbances can propagate across interplanetary distances. Magnetic field fluctuations can couple to Earth's magnetosphere. It's theoretically possible, though unproven, that an actively outgassing interstellar object could create perturbations in the solar wind that reach Earth's magnetic environment. But here's the missing variable that almost nobody is discussing publicly. What if the solar system itself is passing through a region of denser interstellar medium? Space isn't empty. Even between stars, there's gas and dust and plasma, just at incredibly low densities. But densities vary. Our solar system orbits the galactic center, moving through different regions of interstellar space over time. If we're entering a slightly denser region, that would affect how the solar wind behaves. It would affect how cosmic rays interact with the heliosphere. It might affect multiple phenomena simultaneously. This is where LAIC and solar forcing don't fully explain the pattern. You can account for ionospheric disturbances from ground deformation. You can account for electromagnetic effects from solar activity. But you struggle to explain why those effects would align temporally with the passage of an interstellar object unless there's a common forcing mechanism. Unless something is driving both the increased solar activity and the electromagnetic anomalies on Earth. Unless the local interstellar environment is the variable we've been ignoring. Mainstream science is cautious here, and rightly so. There's no direct evidence that variations in interstellar medium density significantly affect terrestrial geophysics. The proposed coupling mechanisms are weak. The timescales don't obviously align, but the absence of evidence isn't evidence of absence. We've only been monitoring these systems with sufficient precision for a few decades. We've only been through one complete solar cycle with modern instrumentation. Our baseline is short. What we do know is that complex systems have emergent behaviors. Multiple weak forcings can combine non-linearly to produce effects larger than any single forcing would predict. Earth's electromagnetic and tectonic systems are coupled in ways we're still mapping. Solar activity modulates those systems. Interstellar objects pass through occasionally. And in 2025, during a year of extreme seismic energy release and high solar activity, a signal appeared at exactly the moment an interstellar visitor reached its closest point. You can call it coincidence. But coincidence is starting to look like the explanation we reach for when we don't understand the mechanism yet. And if history has taught us anything, it's that the mechanisms we don't understand today become the textbooks of tomorrow. When you encounter something that doesn't fit existing explanations, you're left with choices. You can ignore it, you can dismiss it as error, or you can try to construct frameworks that account for the observations. In the case of the December 19th signal and its temporal alignment with 3I Atlas, there are essentially three broad hypotheses people have proposed. None of them are entirely comforting. None of them are conclusively supported by evidence. But they represent the spectrum of possible interpretations. Hypothesis 1 is the null hypothesis. Pure coincidence. Natural, unrelated events that happen to occur near each other in time. 3I Atlas is just a comet, an interstellar wanderer composed of ice and rock and organic compounds, following ballistic trajectories determined by gravity and radiation pressure. It has no special properties. It didn't interact with Earth in any meaningful way. The 25 hertz electromagnetic signal was a geophysical blip, possibly related to tectonic stress, possibly related to atmospheric conditions, possibly a measurement artifact we haven't fully identified yet. The two events are unrelated. This hypothesis has the advantage of not requiring new physics. It doesn't challenge established scientific understanding. Comets pass through the inner solar system regularly. Electromagnetic anomalies occur. Sometimes they coincide temporally. The universe is large and events are frequent enough that coincidences are inevitable. If you monitor enough variables long enough, you'll eventually see patterns that look meaningful, but arise purely from chance. The problem with the null hypothesis isn't that it's wrong. It might be completely correct. The problem is that it's unsatisfying. It asks us to look at a precise frequency, a specific timing, a year of unusual seismic activity, and conclude that the alignment means nothing. That's scientifically defensible. But it doesn't scratch the itch. It doesn't explain why the pattern feels significant. Hypothesis 2 is what I'll call the passive catalyst model. 3I Atlas didn't cause tectonic stress or electromagnetic anomalies, but it served as a modulator or resonator due to its physical characteristics. Comets are not inert. They outgas. They create plasma environments. They interact with the solar wind and the interplanetary magnetic field. These interactions are well documented. What's speculative is whether those interactions can extend far enough or couple strongly enough to affect Earth's magnetosphere or electromagnetic environment. Think of it like a tuning fork. If you strike a tuning fork and hold it near a resonant cavity, the cavity can amplify the sound, even though the tuning fork isn't directly vibrating the cavity walls. It's coupling through the air, through pressure waves, through acoustic resonance. Could 3I Atlas have acted as a kind of electromagnetic tuning fork, creating perturbations in the solar wind or interplanetary magnetic field that coupled to Earth's already stressed electromagnetic system? The physics here gets murky. Coupling efficiencies are low. Distances are vast. The energy required to create measurable effects on Earth from an object millions of kilometers away seems prohibitive. But we're not talking about creating effects. We're talking about modulating existing systems. If Earth's electromagnetic environment was already primed, already stressed, already on the edge of generating anomalous emissions, then even a small external perturbation might be enough to trigger the release. It's like a supersaturated solution. You dissolve sugar in water until it can't hold anymore. The solution is stable, barely, but add a single grain of sugar or tap the glass, and suddenly crystals form explosively. The energy for crystallization was already there. The trigger was minimal. Could 3I Atlas have been that minimal trigger for electromagnetic release? This hypothesis is fringe science. It's not publishable in mainstream journals without extraordinary supporting evidence. But it's not pseudoscience. It's grounded in real physics, just extrapolated into regimes we haven't explored thoroughly. It takes established coupling mechanisms and scales them speculatively. It's the kind of idea that might be right, but will take decades to verify, because the events are rare and the measurements are difficult. Hypothesis 3 is where we enter uncomfortable territory, the active measurement hypothesis. This is the one that makes scientists roll their eyes and conspiracy theorists lean forward. It proposes that the signal wasn't natural at all, that it was deliberate, that Earth is being probed or scanned by something with intention. You can immediately see why this hypothesis is problematic. It requires agency. It requires technology. It requires motives we can't infer and capabilities we can't measure. It's the least scientifically defensible position, but it's also the one that gets the most traction online because it speaks to deeper psychological needs. The need to believe we're not alone. The need to impose meaning on chaos. The need for narrative in a universe that mostly offers us randomness. Some online communities have claimed that 3I Atlas transmitted pulses at 1,420 megahertz in a Fibonacci sequence. This claim is almost certainly misinformation. 1,420 megahertz is significant because it's close to the frequency of neutral hydrogen emission, a frequency that some SETI researchers think alien civilizations might use for communication. But there's no credible evidence that 3I Atlas emitted anything at that frequency. It's a story, a compelling story, but a story nonetheless. However, the reason people latch onto this narrative is instructive. 25 hertz becomes meaningful if you're looking for meaning. Frequencies become codes. Timing becomes intention. The human brain evolved to detect agency. When our ancestors heard rustling in the grass, assuming it was a predator kept them alive more often than assuming it was wind. We're wired to see intention, even when none exists. But let's entertain the hypothesis for a moment. If you wanted to probe a planet's structural integrity, to assess its tectonic stability, to measure its electromagnetic response characteristics, what would you do? You might send a signal at a specific frequency and measure how the planet responds. You might time that signal to coincide with a period of natural stress to see how the system behaves under load. You might use an object that appears natural, a comet, to avoid detection while carrying instruments that can make measurements. This is science fiction. I'm not endorsing it. I'm explaining why the narrative has psychological appeal. It provides answers. It creates villains or benefactors, depending on your preferred flavor of speculation. It transforms randomness into story. And humans need stories the way we need water. Each hypothesis implies a different future. If it's natural coincidence, we continue as we have been. We monitor. We study. We gradually improve our understanding through normal scientific processes. If it's a passive catalyst, we need to expand our models. We need to consider cosmic influences we've dismissed. We need to watch for these alignments in the future. If it's active measurement, then everything changes. Our assumptions about humanity's place in the universe collapse. New questions emerge faster than we can formulate them. The evidence doesn't strongly support any single hypothesis over the others. The null hypothesis is safest, but least satisfying. The passive catalyst is intriguing, but speculative. The active measurement is exciting, but evidence-free. We're left in a state of uncertainty, and uncertainty is where fear grows. Because if we don't know what happened, we can't predict what happens next. We're in the middle of a strange revolution, not the kind with protests and manifestos, the kind that happens quietly in research labs and server farms. Artificial intelligence systems are now detecting patterns in physical systems that human researchers can't see. They're predicting behaviors we don't understand. They're finding signals in noise that shouldn't be there according to our current theories. And this creates a philosophical problem. What do you do when machines see things you can't? 2025 saw multiple breakthroughs in AI applications to geophysics and planetary science. One of the most remarkable came from research at Campi Flegrei, a volcanic caldera near Naples, Italy. Campi Flegrei has been restless for decades. The ground rises and falls. Earthquakes swarm. Geologists monitor it constantly because an eruption would threaten millions of people. Traditional seismic analysis uses networks of sensors to track earthquake locations and magnitudes. You look for patterns. You build models. You try to understand what's happening beneath the surface. Researchers trained an artificial intelligence system on years of seismic data from Campi Flegrei. They didn't tell it what to look for. They didn't program in theories about fault mechanics or magma chamber dynamics. They just fed it data and let it find patterns. And it found buried faults. Structures in the subsurface that traditional analysis had missed. Connections between seismic events that human researchers hadn't recognized. The AI saw a more complex system than anyone had realized was there. This is both exciting and unsettling. Exciting because it means we can extract more information from existing data. Unsettling because it means we've been missing things. Important things. Things that affect how we assess risk and make predictions. If AI can find hidden faults, what else have we overlooked? The pattern repeats across multiple domains. AI systems analyzing electromagnetic data find precursors to geomagnetic storms that traditional methods miss. AI analyzing seismic waveforms detects small earthquakes that automated algorithms overlook. AI looking at satellite data identifies ground deformation too subtle for human interpreters to spot confidently. We're entering an era where the sensors haven't changed, but our ability to interpret their output has exploded. Here's the philosophical twist. We're now in a position where we might predict instability before we understand instability. The AI can tell you that a system is approaching a critical transition. It can quantify the probability. It can identify precursor signals. But it can't necessarily explain why. The model is a black box. Inputs go in, predictions come out. The mechanism remains opaque. This matters for the December 19th signal and the broader patterns of 2025. What if an AI system had been monitoring global electromagnetic data and seismic activity? What if it had seen correlations between interstellar object passages and terrestrial phenomena that we've been dismissing as noise? Would we trust its predictions without understanding the mechanism? Would we even know how to formulate the right questions? There's a risk here that scientists call overfitting. When you train an AI on limited data, it can find patterns that don't generalize. It can hallucinate correlations that arise from the specific quirks of your dataset rather than from universal physical laws. An AI trained on one volcanic system might make confident predictions about another system that turn out to be completely wrong because the underlying physics differ in subtle ways. But there's also the possibility that AI is seeing real patterns that our theories haven't yet caught up to. That the coupling mechanisms between solar activity, electromagnetic phenomena, and seismic events are more complex than our current models account for. That the variables we've been treating as independent are actually linked through pathways we haven't mapped. That what looks like noise to us is signal to a system capable of processing more dimensions simultaneously. Think about how we discovered exoplanets. We spent decades building theories about planetary formation based on our solar system. Then we started finding planets that didn't fit the theories. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Planets with wildly eccentric orbits. Systems that shouldn't exist according to our models. But they did exist, and eventually we updated the theories. The universe was more complex than we'd assumed. We might be in a similar position with Earth system science. Our models work reasonably well most of the time. They explain most observations adequately. But there are edge cases. There are anomalies. There are correlations that appear in the data, but don't have theoretical explanations. An AI doesn't care whether a correlation has a mechanism. It just reports what it finds. And then it's up to us to figure out whether we're seeing truth or artifact. The 25 hertz signal fits this pattern. It's an anomaly. It doesn't have a clear explanation. Traditional analysis would file it away as interesting, but inconclusive. But an AI looking at the full context, the seismic activity of 2025, the solar conditions, the timing with 3i Atlas, might weight it differently, might see it as part of a larger pattern, might flag it as a precursor to something we haven't experienced yet. And this is where it gets psychologically difficult. If a machine predicts instability, do we act on that prediction? Do we issue warnings? Do we evacuate cities? Or do we wait for human understanding to catch up, knowing that by the time we understand the mechanism, the event might have already occurred? We're detecting footprints before we know what made them. We're seeing shadows of processes we can't yet illuminate. And the tools we've built to help us understand the world are now showing us how much we don't understand. AI isn't magic. It's statistics on an enormous scale. But statistics can reveal truth even when theory lags. And right now, theory is lagging badly. Time doesn't care about human anxiety. The calendar advances whether we're ready or not. And as December 2025 fades into January 2026, there's a strange collective tension among the people who pay attention to these things. Not mainstream news, not casual observers, but the communities who monitor seismic data, who track solar activity, who archive electromagnetic anomalies. They're watching a window. The January window isn't an official scientific term. You won't find it in textbooks or peer-reviewed journals. It's a phrase that emerged from online discussions, from amateur researchers correlating dates and events, from pattern seekers looking for cycles in what most scientists would call noise. The idea is that certain gravitational, electromagnetic, and solar conditions align during specific periods in ways that might be conducive to major geophysical events. January 2026 represents one such alignment according to these analyses. Whether you believe in such correlations or dismiss them as numerology dressed in scientific language, the fact remains that people are watching, and watching itself creates a kind of reality. The logic goes something like this. Solar cycle 25 is near its peak. We're in the most active phase of the sun's 11-year rhythm. Solar activity remains high, with frequent flares and coronal mass ejections battering Earth's magnetosphere. Earth's electromagnetic environment is already disturbed, already stressed by months of solar bombardment. The seismic energy budget for 2025 was historically large, but didn't produce a single massive event. That energy is still in the system, stored as elastic deformation in rocks, waiting for release. Various celestial alignments, planetary positions, and solar wind conditions combined during early January to create what some researchers believe is a period of elevated probability for triggering seismic release. It sounds like astrology. It sounds like the kind of thing serious scientists would laugh at over coffee. And many do. Mainstream seismology would tell you this is nonsense. Earthquakes are driven by plate tectonics, by stress accumulation over decades or centuries, by friction and fracture mechanics in rock. They're not triggered by planetary alignments or solar activity. The gravitational effects are minuscule, barely measurable, even with our most sensitive instruments. The electromagnetic coupling is too weak to move rock. You're seeing patterns in randomness because humans are pattern-seeking machines, because our brains evolved in environments where false positives kept us alive and false negatives got us eaten. And yet, statistically significant correlations have appeared in some studies. Not universally replicated, not accepted by consensus, not the kind of thing that gets taught in graduate seminars, but published in peer-reviewed journals nonetheless. Slight increases in earthquake frequency during periods of high solar activity. Possible correlations between geomagnetic storms and seismic events in certain regions. Anomalies in electromagnetic monitoring before some large quakes. The data is messy. The signal-to-noise ratio is low. The effect sizes are small, but the correlation coefficient is not zero. And in science, not zero means something, even if we don't yet know what. The reason extreme events often follow stress accumulation is straightforward physics that doesn't require cosmic forcing. Faults accumulate stress as tectonic plates grind against each other. Friction holds them locked in place. Eventually, the shear stress overcomes the frictional resistance and the fault slips. The slip releases stored elastic energy as seismic waves that we feel as earthquakes. The timing depends on when the critical threshold is reached. Simple, mechanical, deterministic in principle, chaotic in practice. But thresholds aren't always crossed by slow, steady accumulation alone. Sometimes a small additional stress, a tiny push at exactly the right moment, can tip a critically loaded system into failure. Think of a pile of sand. You can add grains slowly, and it remains stable, rearranging itself, finding equilibrium. But eventually, you add one grain, indistinguishable from the thousands before it, and suddenly half the pile collapses in an avalanche. That single grain didn't cause the avalanche. The accumulated weight of all the previous grains caused it. But that final grain triggered it. The distinction matters. This is why even mainstream seismology acknowledges that earthquakes can be triggered by human activities like reservoir filling or waste fluid injection. When you fill a large reservoir, the weight of water increases stress on underlying faults. When you inject fluid into the ground, you change pore pressure and reduce effective friction. The total stress added is small compared to the tectonic stress that's been building for centuries. But if the fault was already near failure, already loaded to 99% of its threshold, that small addition can be enough to push it over. The earthquake that follows releases tectonic energy, not human-induced energy, but the timing was determined by human action. The question is whether natural external forcings, things like solar activity or electromagnetic disturbances, or yes, even the passage of interstellar objects, can play a similar triggering role. The evidence is equivocal. Some researchers think yes, that the electromagnetic and gravitational perturbations, while small, might be sufficient to trigger faults that are already critically stressed. Some think no, that the effects are orders of magnitude too small to matter. Most occupy the uncomfortable middle ground, saying the effects are probably real but too small to matter practically, too weak to serve as useful forecasting tools, too inconsistent to build policy around. What makes the silence after December 19th intriguing is precisely that it's been silence. The signal appeared, the 25 hertz pulse registered on instruments around the world. 3I Atlas passed through its closest approach and continued on its trajectory out of the inner solar system. And then nothing. No immediate catastrophe. No magnitude 9 earthquake-splitting continents. No volcanic supereruption. No global disaster. Just ordinary seismicity. Magnitude 4s and 5s scattered across tectonic boundaries like they always are. Life continued, which could mean the signal was meaningless, a random fluctuation that happened to occur at an interesting time. Or it could mean the response is delayed, that energy relocated within fault systems, that stress patterns shifted subtly, loading some segments while unloading others, that the system hasn't yet resulted in rupture but has changed state in ways we can't easily measure, that the Earth is metastable now, balanced on a knife edge, waiting for the next perturbation to push it into a new configuration. In earthquake mechanics, this delayed response isn't unusual at all. Foreshocks can occur days or even weeks before main shocks, announcing that something is about to give, but not revealing when or where. Slow slip events, movements of faults so gradual that they don't generate felt earthquakes, can redistribute stress without producing seismic waves detectable by normal networks. These slow slips potentially load adjacent fault segments that later rupture catastrophically in what appears to be a sudden event, but was actually triggered by slow preparation. The absence of immediate response doesn't mean the system has returned to its prior state. It might mean the system is transitioning to a new state. The seismic ledger from 2025 is still open. The energy is still there. The bill hasn't been paid. The account remains unbalanced. Solar activity continues. The sun doesn't care that we're nervous. It doesn't read our anxiety or adjust its output to soothe us. Coronal mass ejections still occur, hurling billions of tons of plasma into space. Solar flares still erupt from active regions on the solar surface. The electromagnetic environment around Earth remains disturbed, compressed, energized. If there's coupling between solar forcing and terrestrial seismicity, even weak coupling, even coupling that operates only under specific conditions, the forcing hasn't stopped. The window isn't closed. It's still open. And every day that passes without major release is another day of continued accumulation, another grain added to the pile. This is where human psychology meets geological timescales and creates anxiety that's almost existential in character. We operate on daily and weekly cycles. We plan our lives in months and years. We think in terms of seasons and election cycles and quarterly earnings reports. Earthquakes operate on decadal and centennial cycles. The stress that causes them accumulates over time frames longer than human civilizations. A week of silence after an anomaly feels significant to us. It feels like resolution. To a fault zone, it's an eye blink, less than an eye blink. It's a moment so brief as to be essentially meaningless. Seismic monitoring shows that major earthquakes are often preceded by changes in background seismicity. Sometimes activity increases in a region, with swarms of small earthquakes, suggesting that stress is being redistributed and the fault system is approaching instability. Sometimes activity decreases. The so-called seismic quiescence before some large events has been documented repeatedly across different tectonic settings. The magnitude 3 and 4 earthquakes that had been occurring regularly suddenly stop. The ground goes quiet. Seismologists nervously watch their instruments, knowing that silence can be more ominous than noise. And then, sometimes days later, sometimes weeks, the ground screams. We're now weeks past December 19th. The date has faded from immediate consciousness for most people. The news cycle moved on. 3I Atlas is no longer a trending topic. No catastrophe has occurred. Life feels normal. Does that mean we were worried about nothing? Does that mean the correlations some people claim to see were spurious? Artifacts of confirmation bias and selective attention? Or does it mean we're in a waiting period, that the system has been perturbed but hasn't yet responded fully? That what happens next depends on variables we're not monitoring, or don't understand, or haven't even identified yet. Earth has experienced similar energy upticks throughout its 4.5 billion year history. Periods of elevated seismicity that didn't culminate in singular catastrophic events. The planet is resilient. It has mechanisms for dissipating stress gradually. Tectonic systems are robust, capable of absorbing perturbations without catastrophic failure. Stress gets released through multiple mechanisms, through creep and through slow slip, and through swarms of moderate earthquakes that collectively accomplish what a single giant earthquake might otherwise do. Forecasting specific earthquakes remains impossible with current science. We can identify which faults are capable of large events. We can estimate probabilities over decades. But we cannot predict that a specific fault will rupture on a specific date. All of these statements are true. They're supported by data and theory. They should be comforting, but they're not entirely comforting, are they? Because we have more data now than at any point in human history. We have better instruments, more sensitive, more widely distributed. We have AI systems finding patterns that humans would never notice, correlations across datasets that would take human researchers lifetimes to analyze. We have electromagnetic monitoring networks spanning continents. We have satellite measurements of ground deformation, accurate to millimeters. We have ocean bottom seismometers and infrasound arrays and GPS networks and everything we could possibly want for observation. And with all of that capability, with all of that technology, we detected something on December 19th that we can't fully explain. A signal that appeared at exactly the wrong time to be dismissed as irrelevant. In a year that released extraordinary seismic energy without reaching climax, without producing the singular event that would close the books and reset the system. The scariest signal isn't the one we heard. It's the one we're still waiting for. Because if the Earth was speaking on December 19th, if that 25 hertz pulse was a word in a longer sentence, a syllable in a longer message, then the silence afterwards isn't peace. It's not resolution. It's a pause. It's the intake of breath before the next phrase. It's the moment between lightning and thunder, when you know something is coming, but you don't know how close or how loud it will be when it arrives. We're watching. The instruments are recording continuously, streaming data to servers, filling hard drives with measurements. The AI systems are analyzing, looking for patterns, flagging anomalies. The amateur seismologists are refreshing their USGS pages, checking for updates, comparing magnitudes. The conspiracy theorists are connecting dots, building narratives, seeing intention where probability offers only randomness. The scientists are cautious, choosing words carefully, aware that false alarms destroy credibility, and that uncertainty is honest but unsatisfying. And the Earth, patient as only a planet can be, continues its ancient tectonic dance. Indifferent to our need for answers. Indifferent to our anxiety. Operating on timescales that make human concern seem fleeting and fragile. Temporary as mayflies arguing about the weather. The window is open. The data streams continue. Somewhere beneath our feet, in darkness that light has never touched, in pressures that would crush diamond, stress accumulates. Rocks bend imperceptibly. Friction holds. Energy builds, and we wait, watching numbers on screens, wondering if the silence means safety, or if it means the pause before everything changes.